This PowerPoint will focus on how we find the pH and Ka for weak acids and weak bases, and how that differs from finding the pH for strong acids and bases. So just as kind of a review of the difference, strong acids are acids that dissociate into the individual ions, hydronium and the conjugate base, 100%. And so once you put them in water, there's none of the original intact acid left. And a weak acid is an acid that only partially dissociates when added to water. So you have a very small amount of the hydronium ion and the conjugate base, but the vast majority is retained in the original intact acid form. All right, so again, just as a reminder, it's pretty easy, pretty straightforward to find hydronium ion concentration, pH, hydroxide ion concentration, etc. if you are dealing with a strong acid or a strong base. So, for example, if you were asked to find these properties, values for a strong acid, for example, nitric acid, I usually encourage students to always start by writing a balanced equation for the acidic dissociation in water. Okay, so it's important, very valuable to memorize the 6 or 7 strong acids and bases because you won't always be told that something's a strong acid and strong base. So for example, if you were given this problem, if you didn't know it was a strong acid, you wouldn't know that the concentration of hydronium ion or hydrogen ion is the exact same as the original concentration of the acid that was added to water. And so it becomes very easy to calculate pH. It is simply minus log of that initial concentration of the acid. And the reason we can do that is because the original concentration of nitric acid, a strong acid, equals the hydronium ion concentration because 100% of it converts. And so the pH in this case would just be minus log of 0.30. And so pH of this solution of nitric acid is 0.523. It's quite acidic, isn't it? And then again, just very quickly, hopefully remember that 14 minus either pH or POH gives you the other one. So if we have 14 minus 0.523, we get the POH, and that is 14.3, and that's POH. And then how you get from concentration of hydronium to concentration of hydroxide is the Kw value, 1 times 10 to the minus 14, divided by 0.30, which is the concentration of hydronium. And that will give us the concentration of hydroxide. So let me plug that into my calculator real quick and see what we get. And that tells us that the concentration of hydroxide is very low. 3.3, let's see, what do we have there? 3, 6, 9, 12, minus 14. 3.3 times 10 to the minus, 14 molar. And that is concentration of hydroxide. All right, so I'm not going to go through calcium hydroxide and finding all the values for that because I want to spend the bulk of this on how we deal with weak acids and weak bases. I will remind you at this point, most sources consider calcium hydroxide a strong base. Some of them can categorize it as a weak base, but right here we're going to treat it as a strong base. And what I wanted to point out by showing that as an example, let me change pen colors here, is be careful with the stoichiometry when you're dissociating either diprotic or triprotic acids or bases that have more than one hydroxide. So, of course, calcium hydroxide would dissociate to give the calcium cation and 2 hydroxide. And so that stoichiometry is going to affect your pH and pOH. So just be aware of that. Alrighty, so here's not quite so messy what I kind of crammed in on the last page if you would like to go over. Just to point out here, so follow through on the calcium hydroxide. So we started with 0.0042 molar calcium hydroxide, treating it as a strong base. That means that we are going to end up with 0.0042 molar calcium ion and 2 times 0.0042 molar hydroxide. So the bottom line is our concentration of hydroxide is going to be 0.0084 molar. And so we can go from there to calculate pOH and pH. Alrighty, onward to weak acids and bases. This is acetic acid, and it is a weak acid. We know that because hopefully you've memorized the 6 or 7 strong acids, and anything that is not a strong acid is weak. I also want to point out that this ending, the CO₂H, sometimes it's written as COOH, is a carboxylic acid. That's an organic acid, and they are always weak acids. Alrighty, so again, I always encourage you to start out by writing out a balanced chemical equation. And big question is here, we know that 100% doesn't dissociate. So the question is, how do we find pH if we don't know how much hydronium ion is present? Well, we need more information, right? We need to know what percentage of this original weak acid dissociates before we can know the concentration of hydronium ion. And the value we use to tell us the percentage of dissociation or ionization is Ka. So sometimes that's called the acid ionization constant or the acid dissociation constant. It's a type of equilibrium constant, which we'll learn more about later. But if you have a reversible reaction, like we do with a weak acid or a weak base, there is an equilibrium constant which tells us whether or not this reversible reaction favors the reactant side or favors the product side. So take a look at what the equilibrium Ka expression is. In the numerator are products, concentration of products multiplied by each other. And in the denominator is the concentration of reactants. Notice that water is left out of the equilibrium constant expression. And the reason for that is the concentration of water is a constant. 55.5 molar, I think, is the constant concentration of water. It doesn't change. So it didn't just disappear from this expression. It's actually lumped in with the Ka, which is a constant. So it's worth noting at this point that all liquids and all solids have constant concentrations. So they are never included in equilibrium expressions. So you can see by looking at Ka, though, that if we're given Ka, and there are tables of known values for all different weak acids and bases, once we know Ka, we can figure out the concentration of hydronium ion that the weak acid makes. Also, because Ka has the products on top, has the hydronium ion on top, that means the larger Ka is, the stronger the acid is, the more that acid dissociates and the more H3O it's going to make. So larger Ka means stronger acid and higher concentration of hydronium ion. There are also Kbs for weak bases, And so if we call B just some generic base, which abstracts a proton from the acid, and we can write up an expression for Kb. Again, products on top, as with all equilibrium constants. Water is left out of the equilibrium expression, and the reactant is on the bottom. So similar type of relationship. The larger the value of Kb, that means the more hydroxide there is present, and therefore the stronger the base. There is a relationship between the strength of a weak acid and the strength of the conjugate base it forms when it dissociates. So what I'm talking about here, let me write a generic expression for you. All right, so here's the original weak acid, and here's its conjugate base, right? There's a relationship between the strength of these two, and this chart shows it beautifully. So the stronger the original acid, so all of these are termed strong acids. These are 5 of the 7 or so strong acids which dissociate 100%. And that's why they essentially, for all practical purposes, don't have Ka values, because they, for all practical purposes, completely dissociate. So we'll kind of ignore those for now. But let's talk about weak acid. So the stronger the weak acid, the weaker its conjugate base. So what am I saying? If you have, let's take it to an extreme. Let's say that we have a strong acid, one of the 7 strong acids. And according to this relationship, that means that this conjugate base would be very weak. What does that mean? Okay, so a weak base means that it's not very reactive, right? Non-reactive. You could also say it's stable. Nature likes stable, likes low energy, stable situations. So this would be preferred over this strong reactive acid. So let's imagine we're this weak conjugate base and we try to recombine with the hydrogen ion to remake the strong acid. Well, if we manage to do that, what's going to happen right away? Well, the strong acid is like, nope, 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 nope. And it's going to break that bond again and shoot right back into the ionized. So hopefully you can kind of envision that. But so the stronger this original acid is, the more reactive this original acid is, the less reactive its product or its conjugate base is going to be. And the converse is true also. So the weaker the original acid is, in other words, when we say it's weak, we're saying it's unreactive and it's stable. Okay, so the weaker the original acid is, the stronger its conjugate base is going to be. Okay, and another way to think of that is this stronger conjugate base, which means it's more reactive, right? So as soon as some of this conjugate base is formed, it's going to strong arm or kind of bully this hydrogen ion and say, hey, get back over here, to reform the weak acid. And being weak, it's more stable and it's going to stay here. So I guess enough stories. Alrighty, so we've introduced the concept of Ka and Kb, and there are also pKa and pKb values, just like there were pH values and pOH values. And they have the same type of mathematical relationship. As a matter of fact, P of anything means minus log of whatever that is. So pKa means minus log of Ka. And it's for the same reason. Logarithmic scales are typically used when the values you're working with are either very small or very large, so that you have to resort to scientific notation with these crazy small exponents. And so rather than dealing with these cumbersome numbers, if we use the logarithmic scale, which simply snatches the exponent, we end up with numbers that are more friendly to use. And so they're the same type of relationships between pKa and pKb and Ka and Kb that we see with pH and pH. So let's look at those relationships. This handy dandy chart, which I love, shows you that any one of these four values we can use math to get to any of the other values using the formulas that are given above or below the arrows. And in a similar way, we can do the same thing with Ka, Kb, and pKa and pKb. And so, for example, let's say that somebody gave us the pKa value and we had to figure out Ka value. Well, we would use this formula. Ka is 10 raised to the minus pKa, just as you found, let's say, the concentration of hydronium ion by saying 10 to the minus pH. So similar type of relationships. Now, a couple of relationships that you may not have seen before is if you multiply Ka times Kb, you get Kw, which is at 25 degrees, 1 times 10 to the minus 14. So do you remember that concentration of hydronium ion times concentration of hydroxide ion also equals Kw, or 1 times 10 to the minus 14 if it's room temperature 25 degrees. And also similar to POH plus pH, pKa plus pKb equals 14, just like pH plus POH equals 14. I'm getting tired of this red pen. There we go. So now if we put those two squares together, so we have the pH squares in the middle and the Ka-Kb square on the outside. And there's just one more relationship I want to show here, and that would be the corners, the diagonal corners. That one and this one. And we're not going to worry about buffers yet. That's a later chapter. Alrighty, but I do want you to know that you can find hydrogen ion or hydroxide ion from Ka or Kb. And that's because the expression for Ka and Kb has each of those ion concentrations in them. And we use something called an ice table, which I'm going to start showing you right now, to be able to use math to get the concentration of hydroxide and hydronium ion. So here's a pretty simple example of using an ice table to figure out the pH of a weak acid. And here's a real typical problem. Calculate the pH of a 1 molar acetic acid solution, and the Ka for acetic acid is 1.8 times 10 to the minus 5. And so this in green is the ice table. So initial I stands for initial concentrations of all of the components. C stands for change, and that's how the initial concentrations are going to change during the reaction. And E is the equilibrium or final concentration of each of the components. This is really important, so listen to what I'm getting ready to say here. These equilibrium concentrations are what you're going to use to do your calculations. So they are the most important values that you get out of this ice table. All right, so now remember the expression for Ka. We're dealing with an acid now, so it's a Ka. If we're dealing with a weak base, it's going to be Kb. And so Ka is always products, which will always be, one of them will always be the hydronium ion, and the other will be the conjugate base from the weak acid. And in the denominator will be the concentration of the original weak acid. And that expression is equal to the Ka value we were given in the problem. So now let's see how we fill out this ice table. The problem told us that the initial concentration of acetic acid was 1 molar. You always assume the initial concentration of the products are 0 unless you're told otherwise, okay? Now, the row that says change can be the trickiest one, and it's important, but it can be quite tricky, but it's not in this case. Because acetic acid was originally the only substance present at the beginning, we know that its concentration is going to decrease. So we don't know how much it's going to decrease. So we're just going to call it minus X. And we know from the stoichiometry of this reaction, for every 1 acetic acid, we're going to make 1 hydronium ion and 1 acetate or conjugate base. So because of that, for every X that disappears of acetic acid, we are going to create X amount of hydronium ion and X amount of the conjugate base. Once you have the initial amounts and the change amounts, it's simply a math problem, okay? So for the equilibrium concentration of acetic acid, it's 1 minus X, and simply X for the concentration of the products. So now take these equilibrium values and plug them into the expression for Ka, okay? So 1 minus X goes in the denominator, concentration of acetic acid, and the X's represent equilibrium concentration of the products. So here is our Ka expression with the equilibrium concentration values plugged in. Now we have to solve for X, because what will X tell us? Look here. X is the concentration in the hydrogen ion. Hopefully you know by now that's just kind of a lazy way of writing hydronium ion. They are considered equivalent. All right, this, if you just kept it in this form, you would end up having to solve a quadratic, which we all know is kind of a pain in the patootie, right? So in many, many cases, as a matter of fact, in most cases, it is okay, mathematically okay, to neglect this X that is subtracted. And the reason you can do that is because Ka is so small that it means not very much X is going to form, right? The size of Ka is what determines how much X is going to form. And 10 to the minus 5 is incredibly small. So not very much X is going to form. And certainly orders of magnitude less of X than 1 molar. And so we're just going to pretend like that X isn't there. We're going to neglect it. And so that gets a lot more simple, okay? And so now it's simple to solve for, move that up, to solve for X. Multiply both sides by the denominator, which is just 1 in this case, okay? And then you'll have X squared equals 1.8 times 10 to the minus 5. And then take the square root of both sides, and that is it. So we get that X, which is hydronium ion, equals 4.3 times 10 to the minus 3. Now be really careful when you go through all this work and you solve for X and you think, okay, I'm done, and you go on to the next problem. Go back and read the problem, because normally X is not what the problem is asking for. This original problem actually asked for pH, so we have more work to do. pH is minus log of the concentration of hydronium ion. So there's one more calculation, and there we have our final answer. So the next couple of slides are just kind of a little sideline problem that's often asked when you are doing weak acids and weak bases, and that is percent ionization. That's kind of another way of giving, is another way of giving information about how much of these ions are formed from a particular weak acid or weak base. And so the formula for percent ionization is concentration of the hydrogen ion, or if it were a base, hydroxide ion, over the original concentration of the weak acid or base. And since it's a percentage, times 100. So we know, and to do percent ionization, you typically have to go through the ICE table just like we did. But we know the concentration of the hydrogen ion from the ICE table on the last slide. It's 4.3 times 10 to the minus 3. And we know the original concentration of the weak acid because the problem told us in the beginning it was 1. And so the percent ionization of acetic acid is 0.43. That's hardly anything. That's less than 1%. Okay, so weak acids and weak bases typically do ionize to an extremely small amount. And just a comment, percent ionization, one of the most valuable pieces of information it gives us is it tells us whether or not it is in fact mathematically safe or statistically safe to neglect that x. If you remember on the last slide, it saved us from having to do a quadratic. And so if the percent ionization is less than 5%, that means it is in fact okay to neglect x. If the ionization is 5% or greater, you're stuck doing the quadratic. Alrighty, so here's just kind of a summary list of the steps involved in working through a weak acid or a weak base if you're asked to calculate pH or something similar, in case this might be handy. So again, always start by writing a balanced chemical equation. I like to set up my ICE table right below the chemical equation, okay? Fill out as much as you can in the ICE table. Remember to enter 0 for the initial product concentrations, unless the problem tells you otherwise. Go ahead and write your generic expression for Ka or Kb so that you're ready to plug the equilibrium amounts in when you work through the ICE table. And plug them in. Solve for, if you're asked to solve for a pH, then you're going to need to solve for X, which will typically represent hydronium ion concentration for a weak acid, or if it's a weak base you're working with, X will be the hydroxide concentration. This is another common kind of tweak of a weak acid problem. You are often asked, rather than define pH, you are often asked to calculate the Ka value of a particular weak acid given the pH. So let's look at a problem like that. So here's a weak acid, phenylacetic acid, and really don't get caught up in the chemical structures or formulas of these weak acids. It really doesn't matter how complex the formula may be or not. They all work the same way, okay? So just generically, the weak acid, when you put it in water, you are going to get hydronium ion and you're going to get the conjugate acid. So don't get freaked out by a complex weak acid. All right, so we're going to start the same way. We're going to go ahead and write our balanced chemical equation. As I said before, I like to set up the ICE table right below the balanced chemical equation so that everything's kind of already lined up in columns. Remember that water or any pure liquids and solids do not affect the position of an equilibrium. So we're going to leave that out of the equilibrium expression. The initial concentration of the weak acid, the problem told us, was 0.12 molar. And as usual, unless we're told otherwise, the initial concentration of the products is 0. Now, here's the catch. This makes it actually easier than weak acid problems that ask you to find the pH. They don't give you Ka, but they give you pH. So listen really careful. This is important to understand. The value of pH, or what pH tells you, is the equilibrium concentration of hydronium ion. Okay, let me say that again. pH represents the equilibrium, or the final concentration of hydronium ion in a solution. So that means we don't have to use X in our ice table. I mean, you can if you want and eventually get the right answer. It's just a bit more work. But instead, what we can do is directly calculate the concentration of hydronium ion from the given pH. Okay, 10 to the minus 2.60. If you put that in your calculator, it gives you 0.0025 molar. So that is the equilibrium concentration of the hydronium ion. Now, how do I know that it's also the equilibrium concentration of the conjugate base? I know that from stoichiometry, because for every one weak acid that dissociates or ionizes, I'm going to get one hydronium and one conjugate base, okay, 1 to 1. So I know that these are the same. So knowing the equilibrium concentration allows me to know what the change is, right? Because 0 plus 0.0025 equals 0.0025, pretty simple. And then, of course, since the reactant side is decreasing in concentration, you remember to put a minus sign for the reactant. So doing our math, 0.12 minus 0.0025 equals 0.1175. So now just plug all this into your calculator, and that tells us that the Ka for this weak acid is 0.000053, or 5.3 times 10 to the 10 to the minus 5. That's it. So I think this form is a little bit easier, actually. All right. So let's do a weak base. There aren't enough samples of weak base problems, so students aren't exposed to them as much, so they can kind of tend to freak you out or trip you up on a test. So let's go through one of them, and I would encourage you to practice more on your own too. I've mentioned several times before that neutral nitrogen-containing compounds are often or usually weak bases. That's an important little piece of information to remember. All right, so here's a weak base. Ammonia is the most common one you'll see, the most common weak base. All right, so here they gave us Kb, and they're asking for pH. There are a couple little tricky things you need to be careful when you're dealing with bases. First of all, need to make sure the problem actually gives you Kb. If the problem gives you Ka, but you're dealing with a base, you know what you have to do? You have to calculate Kb, okay? So if a problem gives you Ka and you need Kb, remember how to get it. It's 1 times 10 to the minus 14 divided by Ka. But in this case, I was nice. I gave you Kb directly. You don't have to worry about that. And so the next thing you've got to be careful is, what does a base do when it's put in water? The base, remember they all have lone pairs, abstracts or removes a hydrogen ion from the acid. In this case, water is acting as the acid. And so what you end up with is your original weak base with an additional hydrogen ion, and typically a plus charge. And what's left over from water after the weak base has taken a hydrogen ion, you have hydroxide. So get real familiar with writing this equation. I know you don't have as much practice with it. So as always, write out the chemical equation, set up your ice table right below it, fill in as much as you know. We were given the initial concentration, 1.50 molar, 0 for both products. And let's see, minus X for the reactant, plus X for both of the products. And now let's set up the expression for Kb. I thought I had it here, but I guess not. Okay, so concentration of CH3 2NH2 times concentration of hydroxide divided by the concentration of the original weak base. Sorry, I'm so sloppy. All right, that is KB. And so now we're going to, let me over here, plug in the values we got from the ICE table. So we have X for each of the products and 1.50 minus X for the reactant. And I'm going to neglect X because the KB value is small. Certainly very small compared to 1.5. Something on the order of 10 to the minus 4. Several orders of magnitude smaller than 1.5. So that's pretty safe to do. All right, working through the math. To simplify this, you always want to multiply both sides by the denominator first, right? And then take the square root of both sides. And be careful here, because X, if you're dealing with a base, is the hydroxide ion concentration, not hydrogen ion. And so remember, this problem asks for pH, and most problems will. So can you get the pH directly from hydroxide? No. Okay. So first we have to find the hydrogen ion concentration, right? And we get that by 1 times 10 to the minus 14 divided by the hydroxide ion concentration we just found. So here we go. This is the hydrogen ion or hydronium ion concentration. And now it's easy to find pH. Minus log of this hydronium ion concentration. pH is 12.7, which is what you would expect. You started with a base, right? So it better end up with a pH greater than 7. And just to check our neglecting X assumption, remember the 5% rule? If the percent ionization is less than 5%, we were safe in neglecting it. So that's the formula is the concentration of the ion, which in this case is hydronium, divided by the initial concentration of the weak base times 100. And percent ionization of this weak base is 2%. So we're good to go. We're safe to neglect. That wraps up this video about weak acids and weak bases. And practice, 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 okay? There are a bunch of different ways to word this and different versions of these problems.